Hello and welcome to the first of two videos where I'm going to walk you through getting started with KiCad to design your first PCB. So in these videos we're going to focus on building a full wave rectifier circuit. So I've drawn that up here. If you haven't done the lecture content on rectifiers yet, then please take a step back, do that first and then come back to these videos. But here in LTSpice I've drawn up a simple full wave bridge rectifier that includes 4 diodes, a resistive load at 1 kiloohm, so just modeling a small electronic device, and a sinusoidal source that is representing 12 volt RMS from a transformer. So 17 volt peak when you've got 12 volt RMS and 50 hertz due to mains power. So what we'll do is I'm going to start off by simulating this just so that we can have a look at sort of the input and output as a bit of a reminder of how this circuit works. And then we're going to move over into KiCad and start working on the process of drawing this up as a schematic in KiCad before generating the PCB and working through the layout of that PCB. So starting here, we're going to run a simulation first. We'll just do a simple transient analysis that goes from, let's say, 0 to 0.1 seconds. And we'll just pick a small time step of 10 micro so that it's a nice smooth waveform that we get. Run that. And I've set up the nodes here. You'll see that I've created a VO1 and a VO2, and I've put my ground down here. So in terms of measuring everything here, to measure our source, I can just click here, and that'll measure from the top of the source to ground. And you can see that it looks like we expect it to, about a 17 volt peak. Then for our load resistor here, because it's not actually connected to ground on either end, we need to find the difference between the voltage on the top end of the load to the voltage on the bottom end of the load. And it's also worth noting that this is kind of a useful thing to know as well for when you're measuring physical circuits. Because some sources, like our function generators, are physically tied to earth, so ground is always at that negative rail. Other devices, like most transformers, aren't like that. You can pick a ground elsewhere, but yeah, in this case, if we were using a function generator, it'd be physically tied to ground, and you'd have no other choice but to measure this load as the difference from here to here. So in this case, how would we do that? Well, if we were to just click in one spot, we would get a really unexpected output because that's not actually measuring sort of across the full load. So I'll just delete that trace. The way that we would actually do it is go right click, add traces, and we can write in mathematical expressions. So VO1 will be the voltage at my node VO1 minus VO2. And again, this is how you would actually do it in a physical oscilloscope as well. You'd set one channel up on the top end, one channel up on the bottom end, and you'd use math mode to find the difference. When I run that, you can now see in a terrible color, let's pick a better color. In bright pink now we can see our output of our full wave rectifier, which is that everything has been flipped to be positive, and we've just lost a little bit of voltage off the top due to it being going through 2 realistic silicon diodes. So that's what our circuit's doing. It's taking that sinusoidal waveform and it's converting it to all positive, which could then lead into later steps. And it actually will lead into later steps. I suggest that you follow this demo along as we're going, because if you sort of save all your files here, it'll form the basis for Prac 1, where we're going to use a full wave rectifier as part of a larger AC to DC power supply. So that's our simulation done. Now we want to go over and start actually building this thing as a physical board. So I'm just going to move this over to the side for now and bring up KiCad. So when you open up KiCad, you can create a new project. Actually, I might quickly mention the tools here. There's a fair few tools you can use in KiCad. The two that we're going to be focusing on in these videos are the schematic editor and the PCB editor, which allow us to lay out the electrical configuration of our board and then the physical board itself. But there's other tools here that you might use down the track, like symbol editor and footprint editor, which allow you to change how things look in the schematic editor or PCB editor, as well as things like being able to convert images of schematics into actual images into schematic symbols or PCB footprints. So you can explore those other tools later on, but we're going to focus on these two first. So we're going to create a new project and just save it somewhere. So I'm just going to put it, I'll just put it here. I'm going to create that file. Once I've saved it, then I can open up the schematic editor. And you can see it's just kind of like an empty blueprint type canvas. And we've got lots of tools around our interface to look at as well. So I'll quickly talk through some of the important ones. The ones on the left are kind of largely aesthetic. It changes just sort of the dimensions you're working in and stuff like that. Then across the top, we've got things like being able to edit those symbols. We can also browse the library of symbols. We can also edit footprints. Most of these things you won't be touching in this subject because the stuff we're using is all pretty conventional. One tool that can be useful is the electrical rules checker, and that just allows you to check that everything's electrically connected and valid. There's also actually a Spice simulator built in that you'll see. It's really clunky though, so simulate everything in LTSpice and then move over to here when you're ready to actually build a PCB. Yeah, and then what we'll eventually also use is the PCB editor, where we generate our physical board based on our schematic. Then along the side, we've got stuff for drawing that schematic. So we've got things like being able to place symbols, as well as draw wires, some other useful things like labels and annotations that we can use as well. I feel like the easiest way to see how this works is just to get into it. So I'm going to move this over here and keep LTSpice open, because what we can do is pretty much just copy our LTSpice design that we've already done into our schematic file here. So the first thing I'm going to place is our diodes. I'm going to open up the place symbols panel, so you can click on the little op amp symbol or just hit A on your keyboard. And you can actually search to see if they've got the exact diode we want in the library. And in this case they do, which is convenient because it also means that it'll come with some footprints you can choose from. And in this case, the default footprint is actually a good choice. It's got a decent spacing for a through-hole diode, and you can see the 2 pins there as well. You can also check on this option to place repeated copies, and that just means that once you've placed one diode, it'll automatically pop up with another one rather than having to come back into this place symbols portal to do that. So if I press OK there, I'll zoom in a little bit. You can press R on your keyboard to rotate components. So just go through and do that until you've laid out all of those the way you want them. So now that we've got all of those down, the next thing we might want to do is wire them all together. So we can grab the wire tool, or you can press W on your keyboard, and you can just start drawing them. And that wire tool is going to stay on until we're done with it. So you can also click as you kind of reach a bend to shape it into more of a full boxy kind of a turn like we did at the top and bottom there. And then that's all of our diodes wired together. The next thing we want to do is place a resistor. So again, go into our place symbols, you can click it or press A on your keyboard and just search for resistor, and you'll find just a basic resistive component. You'll notice that there's no default footprint. You can change that here and pick from a fairly long list. I kind of find it's nice to do it with the footprint picker in a separate section. I'll show you shortly, because it allows you to view it in 3D and stuff, which is just a nice sanity check as well. So for now, I'm going to leave it with no footprint. R on my keyboard to rotate, and I'm going to pop it into my circuit here. Press escape to stop dropping resistors, and then W to start the wiring tool. Now our resistor, unlike our diodes, is kind of a fairly generic component, so it doesn't have any properties assigned to it or anything. So what we can do, once I've actually managed to move this out of the way, is we can edit the properties of that resistor itself. So we can change things like its name. To get into that edit panel, you can right click and click properties, or you can press E on your keyboard. Once you're in here, you can change things like the name. So I can call it L1 to specify that it's a load resistor. It does like to have a number on the end, so leave the 1 there. You can also assign a value, which is useful when you've got like lots of resistors on a design, because you can use that value to actually engrave or silk screen the value. That way when you're going to solder things in, you don't have to kind of come back to your design and try to figure out which resistor was which. You can just kind of look at your board and go, oh, that was my 1K, solder that in there, and so on and so forth. So in this case, it doesn't really matter. We've got one resistor. You can just remember that that one needs to be 1K, but we can still put it in there. And then there's the footprint selection part. So if you click on the little bookshelf, it's going to open up the footprint chooser. And the footprint chooser allows you to filter by the component type as well as by pin count. Those settings will probably be on by default, but if they're not, just check them on. And that'll just mean it narrows it down to only things that are resistors and only things that have 2 legs. Then we've got a few options. We've got optical devices, we've got surface mount resistors, and we've got through-hole resistors. Because we're doing a through-hole board, we want all of our components to be through-hole because we're going to mill them in-house. We're going to drop this down and just try to pick one that's suitable. And suitable is kind of subjective. I mean, we want something that's got a little bit of spacing between the 2 pins so that we can put a standard sized resistor in. So probably something that's at least 7.62 makes sense. And then the other kind of thing will be the width. So you can see this first one here is quite narrow, and it says it's intended for a 0.167 watt resistor, so that'll be quite small. I would probably pick this one as my minimum. That's for a 1/4 watt resistor, so it just gives you a little bit more clearance when you go to do your layout for a thicker, more standard sized resistor. Actually, the other thing I forgot to show you there, if we open that back up, you can also do the 3D view like I mentioned. So I'll just check on to show it in its own window because it makes it a bit larger when you do that. And it just means that you can look at where the component actually is going to be, how it would look on the board, and it's just a bit of an extra sanity check that it is doing what you want it to do. So I'll press OK on that. That's all we really need to change here. So I'll press OK, and that's our resistor in. Now, the other thing that we'll want to add is a way to connect the power supply in. So our power supply will be a separate standalone unit, but we need to wire it into this so that we can actually deliver power to the circuit. So what I'm going to do for that one is I'm going to add in a connector for that. So I'm going to go back into my place symbols library, and there's a couple of different connector types actually. So there's terminals, like screw terminals, where you put your wire in and you use the screw to secure it. But I'm just going to go with the simpler pin type connector. So we can grab the 1x2 pin that has both the positive and negative rail connections, or you could do 2 1x1 pins if you wanted to space them further apart or something like that. But I'm happy with just the 2 pin together. So I'm going to pick that one and I'm going to pop that in there. And then I'm just going to wire that one in, W on my keyboard, to connect it up to everything else. I'm also intentionally not going to assign a footprint, so I'm going to intentionally leave that blank. The reason I'm going to do that is I'm going to show you the error that happens if you forget to assign a footprint and how easy it is to fix. So yeah, I'm just going to leave that there as an intentional error and we'll come back to it. Now, the next thing I'm going to add, I might full screen this at this point. The next thing I'm going to add is the ground. So before in our LTSpice, we had the ground at the bottom, but when we're designing a PCB, we're not constrained by where we put the ground. In fact, it's often useful to put our reference plane, our ground plane, somewhere that there's quite a lot of connections or somewhere that will be important to measure. And the reason for that is it just makes it a little bit easier for starters because you don't have to draw as many pathways to connect all of the things that are connected to the same ground point together. And the other reason is that by using a ground plane, it actually improves some of the electrical characteristics of the board as well. So it makes it perform a little bit better. So I'll sort of show you what that ground plane looks like in the next video, but for now what we're looking for is somewhere that has quite a few connections and somewhere that's potentially going to be useful for our measurements. And in this case, that would be this junction at the bottom of our load resistor between the 2 diodes. We've got 3 connections there, and it'll make it a little bit easier to measure our output if we have a big ground plane as one of our ends and our other end is the top of that signal. So 2 ways we can add a ground. Either you can go into the place power symbols library, which has sort of a short list of stuff that just relates to power. The other thing you can do is just go into the standard place symbols library and search for ground, and you'll see that there's quite a few there. So I'm going to pick that one. I'm just going to drop that one there. I'm just going to move that label up a little bit. It's a little bit easier to click and move stuff if you just press M on your keyboard while hovering. It just makes the selection a little bit less buggy, I've found. So yeah, I'd recommend that. The other thing with ground is if we run the electrical rules checker, you'll see that it gives a strange error where it says input power pin is not driven by any output power pins. And what that means is you've got a ground, but KiCad doesn't know where the power will be coming from, which is fine because it's normally going to be some sort of external power, right? But it comes up as an error. If you want, you can simply ignore that error. If you're like me and you don't like seeing the red text, then you can also fix it by adding in what's called a power flag. So if you go into the place symbols library and just search for power flag, this just gets dropped straight on top of the ground, and all it does is it tells KiCad to not panic, that there will actually be power here. You can ignore this problem. So then when I run the electrical rules checker again, the error goes away. So that's a weird error. I might also show you with the electrical rules checker where it's useful if you make a genuine error. So for example, let's say that I delete this wire. Let's say I'd wired this bottom one in and I hadn't quite gotten all the way to the bottom, and so there's actually a loose connection there. If I were to run the electrical rules checker with that error in, then it would give me an error with some arrows that point to where I've had the problem, and it'll tell me what it thinks has happened. So it says pin not connected, unconnected wire. Why it does that is both a warning and an error, don't know, doesn't really matter, but what we can do is we can then add our wire in, run that electrical rules check again, and it'll go away. Our circuit is now electrically valid. So perhaps not super useful for a small circuit like this, but if you're making a more complicated circuit like the one for your assignment or something like that, it's just a good sanity check that you haven't, forgotten to wire something in or something like that. So all together now, our schematic is looking pretty good. Again, the one thing I have not done is assign a footprint for this. So I'm going to intentionally create an error here when I move over into creating the PCB. That way I can show you how to fix it if it happens to you. So we're going to now click on the PCB editor button to start that process. It'll have a little think while it switches over. And again, we get like this blank blueprint type of a canvas to work with. And at the moment, there's nothing on it. So to actually get the components over here, we need to click this button here of Update PCB from Schematic. You can see it gives us an error, cannot add J1, no footprint assigned. So that's that error that I intentionally left there. You can click that again later on to check if any errors have been resolved. Once you close that, it'll give you all of your components to drop onto the canvas. So at the moment we've got 5 components because I need to go back and assign that footprint. So we've got our 4 diodes and our load resistor. So now I can go back and fix that error really easily. I can just go back to the schematic editor. I can click on or hover over my connector, press E on my keyboard or right click and click properties. Now I can set a footprint and again, filter it by connectors. The first option is pin socket connectors. So there's 2 here that are surface mount. We don't want those, we want through hole. And of the 2 through hole options, the vertical one looks nicer to me, so I'm going to go with that one. Actually, we can also, if we want to take a bit of a look at what that would look like in 3D, we can bring that up and you'll see that it's just a basic 2-pin header that you could wire some jumpers into or something like that. So I'm happy with that one. Click OK again. Now we just simply go back to our PCB editor and go through the same button process. Update our PCB from Schematic. You can see that now there are no warnings. Need to hit the update PCB button again. So no errors, no warnings. Close that and it'll give me my new connector to drop in. So now we can see that all of our components are on the canvas. They're a jumbled mess. There's no connections between them or anything like that. I'm going to leave this video here though, and we're going to have a look at the problem of actually laying out our PCB and some PCB design tips and tricks in the next video. So I will see you in that one.